That is the Carnot cycle. As we mentioned earlier, that is expand, isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression, going from a high temperature to a low temperature. Now, as we mentioned, the area bound by these curves represents, and on my tablet here this is not displaying, but I notice on Canvas it's displaying just fine. The work produced by the Carnot cycle. Okay? So the net work, because this is a cycle, net work out, we can put a cyclic integral here. Closed interval integral. Meaning I'm going to integrate this from an initial state and I'm going to finish back at that same initial state. From V1 to V1. Pressure with respect to volume. Now, because integrals are just sums, they're infinitesimally small sums, but they're sums. So what that means then is that this net work out is going to equal then, I can break this up into its parts. So I can say, well, add up this amount of energy here. Right? So the integral from 1 to 2, pressure with respect to volume, plus from 2 to 3, integral from 2 to 3, pressure with respect to volume, plus integral from 3 to 4. I'm putting these in the wrong place. Oops. Starting at 2 going to 3, starting at 4 going to 3, I'm sorry, starting at 3 going to 4, pressure with respect to volume, plus integrating from 4 going back to 1, pressure with respect to volume. Getting us starting at state 1, finishing at state 1. It's a cyclic integral. That's what the net work out from this cycle, what we can produce from this cycle. Notice the sign of each integral. This one's positive. This one's positive. This one is compression, therefore it's negative. This one's compression, therefore it's negative. Right? I'm integrating from initial to final volume. If it's expanding, I will get a positive quantity. If it's compressing, I will get a negative quantity. And that's what I was doing up here, right? Add this amount, subtract this amount, subtract that amount. That sum gives you this area bound by the curves. The area equals the net work out. The work produced by the Carnot cycle. Okay. And this diagram you'll typically find in a textbook, something like this. Saying we'll put the heat in up here or during the constant, so add heat as it expands to maintain a constant temperature. Remove heat down here as it is compressed to again maintain a constant temperature. The area bound by the curves represents the net work you can generate or extract from the engine for the cycle. Okay. So this is a terrible graphic. At least it's a terrible scan of a graphic. It's not a bad graphic. This is a graphic they use in our text. They're showing you could do this, you could try to mimic this with a piston cylinder, add heat, and allow the system to expand, allow it to expand when you insulate the entire thing, do it adiabatically, and then from the highest, largest volume, begin compressing, allow it to reject heat so it maintains a low constant temperature, and then continue to compress it so it reaches the higher temperature and it's ready to repeat the cycle. So you could possibly do this with a piston cylinder in an ideal condition. We don't have any engines that operate anything close to a Carnot cycle. Okay? But it was one of the first examples of a reversible cycle that shows up in the literature. And it became kind of the limit, one of the first limits, one of the first best case scenarios of an engine that shows up in the literature. Right? Because by definition of the Carnot cycle, all these processes must be reversible. And so if we do the reverse of all the processes, we get an object that then is removing heat from a high temperature body, removing heat from a low temperature body and exchanging that heat, adding that heat to a high temperature body. It reverses the direction of the heat flow. We call that a Carnot refrigeration cycle, which you see here, right? So here we reverse the cycle. Now we're going to expand, compress, compress. We're doing the same process. We're just doing it at different temperature limits. So that allows, we're putting work in, right? Here we're compressing across the top. So these are negative quantities on top. These are compressions. That's work in. And during what happens then is we reach this high temperature up here. To get from 3 to 4, we reach this high temperature, so we can lose heat at a high temperature. And then we expand down to a cooler temperature, and then we can absorb heat from the low temperature and go back, which is essentially what a refrigerator does. And so what we're saying is this is kind of also the best model we have for an ideal refrigerator. This kind of is the limit of a refrigeration cycle. How good can our refrigeration cycle be? So a couple of things come out of the Carnot cycle, right? The development of the Carnot cycle. Two main corollaries, two main statements here. One is the efficiency of any irreversible heat engine. Any heat engine you or I would construct. The efficiency of an irreversible heat engine is always going to be less than the efficiency of a reversible engine if it's operating between the same two temperatures, or the same two reservoirs. So to go back here, right, this means this engine or this refrigerator is absorbing heat from somebody down here at a low temperature, and it's exchanging heat or rejecting heat out here at a higher temperature. Right? And on my paper here, I've drawn an engine. This one is absorbing heat at a high temperature, and it's rejecting heat at a low temperature. So in both cases, it requires, just like the heat engines and refrigerators we've already drawn, two reservoirs with which to exchange heat. One of the main Carnot principles is saying, look, the efficiency of any actual heat engine, an irreversible heat engine, operating between the same two reservoirs, exchanging heat with the same two reservoirs, is going to be less efficient than this reversible Carnot engine, the Carnot cycle. And the other thing, the really important thing that comes out of this is the idea that the efficiencies of all reversible engines operating between the same two reservoirs is the same. So if I have a device operating in a reversible fashion, a reversible engine, that engine is the most efficient engine that we can build. That's the limit. And the only thing that's controlling its performance is the temperature of the two reservoirs with which it operates. So the efficiency of a Carnot engine, right? Carnot engine, I'm going to put ink in here and say status or any reversible. So not just a Carnot heat engine, but any reversible heat engine is only dependent on the temperatures, TH and TL, the temperatures of the high temperature and low temperature reservoir. I gotta tell it I'm done with ink. Alright, so give me a second here. For some reason my tablet's not displaying these. Okay. So I'm going to have to stop there and figure out what I've got here. So hang on. I'll be right back.